something new topic. We have been dealing with electric fields, of course, and that's pretty much been the focus of the first 3 chapters here, just how electric fields affect matter, how charges create electric fields, and how to calculate electric fields using superposition for charge distributions and so forth. We want to now turn, so electric field, and from the formula we have to memorize it right, electric field we can define as the force per unit charge. If you have a charged particle, you measure the electric force on it, and you find the electric field at that location. And it's kind of nice because then you can take that particle away. Okay, so you have a positive charge here, and you know the force on it. And if I take the charge away and just look at that observation location, if a positive charge had a force that way, I know the electric field has to point at that direction at that location. So then I can put any charge I want there. I can place a negative charge there. I know the electric field. I know the force would be in the opposite direction. I place a charge of a different magnitude or there. I could find the new force on it. Okay, so it's useful to have a quantity that's electric field, or that is electric force on a per charge basis, because then you don't care about the specific situation. You have a much more generalizable concept. Well, what we're going to do in this next chapter is apply the same type of idea to energy, okay, rather than forces. We're going to be thinking about energy and energy per unit charge. And let's just do a quick review, sort of the basics of energy, if I can spell it. Okay. Let's just look at the energy of a particle. So here's a particle. It has some mass, and it's moving with some speed in some direction. And we can write out its energy. And those of you who took 205M, what's the most general expression for the energy of a single moving particle? It's gamma m times something, c squared. Yeah, gamma m c squared. What's gamma? Yeah, good. A lot of people remember it. 1 over the square root of 1 minus v over c squared. So this is the full, relativistically correct energy of a particle that comes out of the Einstein's theory of relativity. And we oftentimes break this expression up into 2 pieces. We can talk about the energy of what's called the rest energy, or just the energy from the mass, which is mc squared, plus the energy of motion, which is called what? Kinetic energy. Okay, so that's plus k. So we have rest energy plus kinetic energy. Okay, energy of a particle. So we then think about, well, okay, that's great, but we need a principle. We need a way to say how energy changes if there are interactions, okay? And so the energy principle for a single particle, ignoring multi-particle systems, is just going to be the change in that energy being equal to what? What goes on the other side? Anybody remember? Change in energy is equal to work. Yeah, work. Okay, if you might have seen it called energy principle or conservation of energy, or sometimes it's called the work energy theorem. Goes by a number of different names, but it's basically saying if I do work on a system, the energy is going to change in some way. And what's work? Work is defined to be what? Okay, force times distance. How do we multiply the force with the distance? There's a special way of, say again? Someone said it. It's a dot product. Yes, thank you. Very good. Dot product of F, the force, and the displacement. And this is just for a constant force. I'm not going to worry about non-constant forces for right now. So for a constant force F dot delta R. What is a dot product? I have Fx, Fy, Fz dotted with delta x, delta y, delta z. And so if I do the dot product, what do I write? Fx delta x plus Fy delta y plus Fz delta z. Okay? And it's a scalar. It's not a vector. It's a scalar, right? It just gives you a positive or negative number. And energy is a scalar, too. It's just a number, okay? So let's actually apply it to a very simple situation. You have a ball or something, mass of some sort, and you drop it so near the ground. Okay, so here's the Earth, and here's a ball, and it has some mass. And it falls some distance, h. And you want to find how much the energy has increased until just before it hits the ground. Okay, so some distance h, and we're looking at how fast it's moving or what's going to be its energy right before it hits the ground. So the force, what force is acting on the ball? Gravity. Okay, so we can write that as a vector, right? We can say the gravitational force is pointing downward. That's going to be 0. We assume that this is the positive y direction. Up is positive y. Force is going to be 0, negative mg, 0. The displacement, the change in position, is going to be 0. What? What's the displacement in the y direction? Negative h. That's right, negative h. 0. So we can figure out the work, right? The work is going to be work done by the Earth on the ball. F dot delta R is going to be, well, 0 times 0 plus a negative mg times a negative h plus 0. So this gives us a positive mgh. And so we can say that the change in the energy of the system is positive mgh. And if I write this out in terms of rest energy and kinetic energy, does the mass change here? Is the mass of the ball going to change as it's falling? No. Okay, so it's just going to be a change in the kinetic energy. And so we'd have, so just being very detailed, delta mc squared plus k is mgh. And so the mass doesn't change, so we just have delta k is equal to mgh. Okay. Mass is positive, g is positive, h is a positive number, like 1 meter or something like that. So what happened to the ball's kinetic energy? It went up. It increased, right? And so if I let something from rest, as it falls, it's going to speed up until it hits the ground. And we're looking at just before it hits, right? So it's moving faster at the bottom than what it did at the top. And it makes sense because the force and the displacement are in the same direction. The work is positive. Positive work means positive change in energy. Energy has increased. Okay? Not very surprising. We could choose a different system. Okay, so the system that I implicitly chose here was just the ball. Okay? But you got to be careful when you're choosing a system, because it may change how you analyze the problem. So what if we chose a system that was the ball plus the Earth? Same situation. So what happens? We have the change in energy of the system is equal to the work done. What happens here? Anybody remember? What's the work in this case? The work is 0. Why is it 0? Well, the kinetic energy, the ball still speeds up, so the kinetic energy is still going to change. Okay, there's nothing significant outside the system. Okay, so the work here is, this really means the work due to this from the surroundings, right? And if we have a system that consists of two bodies and there's an internal interaction, we don't just have kinetic energy, we also have something else. We have potential energy, right? And potential energy comes from, if we wanted to find out what this internal work would be, well, the internal work would be the same as what was the external work, or the work by the surroundings in the previous choice of system. The internal work is going to be mgh. But we define a quantity called the change in potential energy to be equal to the negative of the internal work. Okay? So we would have the change in kinetic plus the change in potential equal to the work done by the surroundings, which is 0. This says that the change in kinetic energy of the ball minus the work internal, which we just found to be mgh, is equal to 0. And we can solve for delta k and get the same result. Okay, so our result hasn't changed, our choice of system has. But it tells us that if you have a potential energy, if you have an energy which is an internal interaction, okay, potential energies are energies of interaction of particles within a system. And if you have a change in potential energy that is negative in this case, delta U is negative mgh. So what happened? Well, we let the ball go, and it just fell on its own, right? So if I have a negative change in potential energy is going down, that's telling me something that can happen sort of spontaneously, right? It'll just fall on its own. I don't have to do anything to sort of change external to change that potential energy, and the kinetic energy will just increase. What if we had a different situation? What if we had a case where the ball was initially moving with some speed upward, some velocity in the upward direction, and it moves up some height h. Okay? So what changes here? What would be the sign of the change in potential energy in this case? It'd be positive, right? It's getting farther and farther away, so delta U is greater than 0. Delta K would be decreasing, right? So delta K would be decreasing, so delta K would be less than 0. So here's a situation. We look at the sign of the potential energy. The change in potential is going to be mgh in this case, positive mgh. And so delta K plus delta U equal to 0. Again, I'm using a system of the ball and the earth. Okay. Delta K is then going to be negative delta U. Delta K is negative mgh. Kinetic energy goes down. Again, it makes sense, right? It's going to be slowing down as it moves upward because the gravitational force is downward. The displacement is upward, so that's our delta R in this case. You take the dot product of the force and delta R. If they're in the opposite direction, those two vectors are in opposite directions, then the work is going to be positive or negative. Two vectors, opposite directions, take the dot product, gives you negative, right? So if I chose the system of just the ball, look at the other situation, or the other way of analyzing this, delta K plus the work due to the Earth. If the work due to the Earth is negative, then delta K is negative. It's slowing down. Okay? Okay, so we get the basic idea. All right?